Good morning, dear colleagues. Now I will share my screen. Our presentation is about Markov model for availability assessment of PLC in Industrial IoT, considering subsystems failures. Presenter is Marina Kolesnik from Department of Computer Systems, Networks and Cybersecurity of National Aerospace University, Kharkiv, Ukraine. Axel Jansch, Institute of Information Technologies of Vienna University of Technology, TU Wien. And Irina Peskachova from State Biotechnological University, Kharkiv, Ukraine. The new technologies.
For example, the structure scheme of IoT
Sorry.
Please continue.
Yes. The new technologies, such as industrial Internet of Things, include different subsystems. You can see here the structure scheme of IoT system. This is not mine, but from famous source. And you can see here the place of PLC inside of complex system IoT, which consists of different sensors, light, motion, humidity, smoke, door environments, cameras, robotics, computer-controlled machines, IoT gateways, firewalls, and also PLCs. Not only the one, they can be in large number at the IoT system, and also special software for management SCADA systems and PLC systems, also special software like operation systems, like Linux. And the functioning of the IoT subsystems depends on dependability and availability of its subsystems. We can see examples of large modular PLCs from different producers, which can be connected to the IoT system like network device. And the structure of the large modular PLC, you can see in the figure 3 that it includes system components, service components, operation system, firewalls, different protocols, input-output components, global data space, and different communication protocols. And the goal of our research is to develop and to research evaluation Markov model of PLC availability. And for this, we used system analysis of structure of PLC system and used different states of and conditions of different subsystems. Assumptions for the developed model you can see at the slide, and availability is an important property of PLC dependability. We will choose mathematical apparatus of Markov modeling to assess availability of PLC. And novelty of this research is an assess of PLC, like development of availability model for its structural subsystems, and assumptions like means of monitoring, diagnostic, verification, and validation are reliable and correct, determine the technical condition of the PLC. The process occurring in the system is a process without after effect each time in the future. The behavior of the system depends only on the state of the system at a given time and doesn't depend on how the system came to the state. The flow of PLC's hardware failures and also its subsystems is the simplest, random, and obeys the Python distribution law. Also, we can say about PLC software, we include software failures also in our model. And its flow is the simplest, also random, and obeys to the Poisson distribution law. And failures caused by errors in the PLC software and its subsystems also obeys Poisson distribution. Secondary error is corrected based on the result of validation and verification, and until the software failure is fixed. And we consider the number of primary defects in the software to be constant. Therefore, the failure flows of the PLC subsystems and the entire PLC have the Markov property. Our paper considers a PLC system that contains several subsystems. We used only main subsystems of large modular PLC. They don't change their position, they are static systems. So we describe PLC like static system. Communication protocols and software which are used for PLC functioning are also considered static subsystems. Wherefore, to assess the availability of the PLC can be used the stationary coefficient of availability. We use such indicator and to understand and to simulate our model and to understand what different stages and failures of different component subsystems of PLC will influence the availability coefficient of our PLC. Also, the graph of a Markov model is presented in figure on the next slide, and the states of a Markov model show states of PLC subsystems and transition rates from one state to another. We decided to assign failure rates like lambda and recovery rates after the failure like mu. Values of recovery transition rates were obtained with the time schedule tools for recovery maintenance after the failure. We had such project from Ministry of Transport, and with timing obtain different rates of recovery for such systems. Also, it was presented. Sorry, I have to escape and to go because I used some slides. The Markov model of PLC availability you can see at the figure on this slide. Each of these states can be, you can read in the 9th and 10th slides, and we used states of execution and synchronization manager, failure state of restart button of ECM, the second version, resolved version, random access memory, read-only memory, SD card, processor core the one, processor core the second, and failure state of two processor rates. Also, Profinet controller failure, Ethernet adapters failures, Exoline F master, GDS module, OPC UA server, special software Profi Cloud, operational system Linux, and special software PC works engineer, also web server, internet user component, Wi-Fi adapter. And we can see that we can obtain the coefficient of availability using initial data of transition rates for the model simulation. We used average values of rates of failure according to statistical data, and also we can change this data using real statistical data from IoT system and from PLC which used in smart factory. And initial data of recovery rates for the model simulation we used with using these results of research in the real at real factory, at real for the real project. And results of the model simulation you can see in figures 5 and 6. And we can see that analysis of graphical dependencies of availability coefficient shows that the value of availability coefficient is high, but not enough because we have only 4 nines after 0. Requirement for PLC availability coefficient is 5 nines and 5. And no, this is complex system, and we used average statistical data. So with real statistical data, we can use more accuracy results. And also we can see a result of simulation of changing failure rate of random access memory. And we can see that the value of availability coefficient decrease in 100 times with increasing of this rate to 0.001. And also we can see such changing with failures with changing of processor core failure rate. As a result of the model simulation, we obtained values of probabilities. Each of states, like failure state of subsystems, can be defined with its probability. And we see that probability of good working state is high, but not enough, because the normative value of AC is 0.9999905. So, according to the Markov model of PLC availability simulation, increase of the failure rate of PLC subsystems can decrease its availability and its dependability. We saw that in 100 times. Our paper proposed an availability model for a large modular PLC of the latest generation, and it can be considered like network device inside IoT system. When constructing this model, mathematical apparatus of Markov models and method of system analysis were used. The study of the obtained model made it possible to calculate the value of the stationary coefficient of availability and its probability of being in each of the states. Obtained results of the simulation indicate that the PLC is a reliable system, and the probability of failure of its subsystems with initial data which we used is small. Our further study will about different impacts of factors on this system, and such like cyber attacks. Thank you for your attention, and we would like to say acknowledgement for National Academy of Sciences in Austria because they support our research in the project of joint excellence in science and humanities. Thank you very much. Tell me, please, your questions.
Thank you very much, Professor Kalysniuk, Marina. Thank you very much. Very interesting, your lecture. Please, have you any questions, please? Yes, Professor Alchenko.
Marina, thank you very much for your presentation. We a lot of time discussing these topics. Thank you for your research. My question is about assumption for Markov apparatus application, because it's really it's not simple question. And in the framework of your report, you said about only failures caused by hardware, yes?
In this model, we used failures caused hardware and also software with, and I have assumption about that primary errors has constant value, and also that secondary flow of secondary errors until the recovery, until the failure of software obeys Poisson distribution. No, in our research, Poisson distribution we assumed.
Okay, it's a standard approach, and concerning software, in this case, we understand that any design faults we can tolerate by restart of system, yes? Not changing of code.
Yes.
And application of patch and so on, yes?
Yes, in my assumptions, I said about that patches or different recovery of primary failures doesn't use here. So we assume that number of primary errors is constant and without changing. So like static variant.
Okay, thank you. And one more question about maintenance procedure. I mean, you very detailed analyzed PLC structure, yes? And
not very, because
according with your model, I think it's a very detailed model. You analyze different components of PLC, yes?
Yes, it was structural analysis because before this research, I made analysis of structure, system analysis of structure of PLC. And also I made analysis of vulnerabilities on each of main components of it. And also like further research now, this is Markov model of availability because we use such subsystems that can be vulnerable, and our research like include some research parts without cyber attacks, with cyber attacks, and we compare how cyber attacks can influence on reliability of it. Now we use only failures of software and of hardware, and in further research also we use cyber attacks, we compare it, and we propose method how to use information about vulnerabilities, models of availability of subsystems in PLC, and also with using cyber attacks model. And we propose method how to to consider all of this and to make recommendation.
Sorry, but it is your future research, and I understand your future steps. My
Yes.
question more simple. I mean, is it in practical issue possibility recovery components of PLC?
Mhm. Yes, but all of these components can be recoverable, and we discussed it with producer of large modular PLC. No, for example, PLC Next from Phoenix Contact, and all of these components can be recovered.
Thank you.
Thank you very much. Any more questions, please? Okay, no more questions. Thank you very much.
Thank you.